Yo, so last time we did pendulum control using a shooting method using an automatic differentiation framework, which is fine, but in reality there's better ways of doing it. So for a bit of a different thing today, I thought we'd just implement this paper, or parts of this paper. We'll see how far we get. And we're going to do it with NumPy first, which should be easier to follow, and then I'll port it to my automatic differentiation framework at the end and say why that might need to change in the future in terms of design, and that might be what we just end up doing next week. Okay, so first maybe a quick recap of what we're doing. This is the board from last time. We've got our pendulum, and we'll move it slowly to a new board. I don't know if it's if I delete this, is gonna, yeah, it is gonna. We're gonna maybe get rid of some of the stuff from here that we're not gonna need. This is what we did next time, or last time, and we'll keep it to this time. Okay, so we've got a pendulum, and what we're trying to do is swing the pendulum up. And what we said last time is we're going to model it as a list of states and controls, where the states are going to be the angles and velocities, and the controls are going to be, well, one control force applied to the pendulum here. And we're going to represent this as a function. And this function is going to tell us where the pendulum is going based on where we are and the force we've applied to it. And this gives us this sort of a computational graph. Let me get rid of that, don't need this today. So gives us this computational graph where we start at x0 and apply some control u0, and that gets us to x1 and so on. And then we use the automatic differentiation framework to give our gradients backwards from the last state, but really backwards from the loss. And our loss is, there's two terms to it. We said it's going to be distance to the target, and the target is going to be at the top here. And then it's also going to give us, also include a control cost, which is going to be the u squared. Actually, we didn't include that here, but in the end we also had u I squared for all controls. And if we go back to the code we wrote here, this is the code from last time. We wrote the dynamics here, then we unrolled our states, and we said this is our loss function. And actually we simplified it. Instead of having the loss be squared, we used the cosine cost. And if you want to know more about that, you should watch the last video. And then we said this is multiplied by some big number, and then it's also adding the velocity at the end because we want the velocity to be 0. And so this velocity term here makes sure that we stop the pendulum without, at the end state the pendulum stops with 0 velocity, and this ensures that it's at the upright position. And then we have some control cost, which in this case is just u squared, and this ensures that we don't use maximal u inputs. Basically lets us do swing up like this, where we slowly build up momentum and go to the top. Now this is fine as a first attempt. The problem with this kind of optimization, and you can see here it takes a lot of iterations, this is not the best way of solving this problem. And in fact there's a better way, and that's what we're going to do today. So we're going to implement differential dynamic programming. Actually, what we end up implementing is called the iterative linear quadratic regulator, and very closely related. You can see here in this paper, this exactly the same modeling that we did. So we say the next state is the function of the current state and the control, and then we have some sort of cost, and this cost is the intermediate cost, and then some final cost. We go here to our board, we have our final cost. This is our x minus target, or realistically, because we changed this, it's going to be 1 plus the cosine of theta, or x theta final, I suppose. This is going to be our last cost, and you can see here we implemented it like this in the code. So that's our final, and then our intermediaries are going to be just these u squared. Then the paper, what it does is it says that this is the minimization that we're doing over the u's, and that's exactly what we did last time. See, we're changing the u's, we're minimizing over all of the u's, all of the controls, and then this is the definition from a state to the end. And what it does is we're not going to get into these bits. We're going to code it first, and then if there's time, maybe next time we'll go through what this means. But it defines this value function, cost to go from each state to the end here, and then it minimizes that. And really what it does is it computes this quadratic approximation, and then you plug this into that, and when you get a recursive relationship, you get these, and you solve for that, you get these equations. But we're going to just take this for granted. We're just going to implement it today, and we're going to implement this and that, and also these things called gains here. So we'll start at the top, and there's a few things we need here. So this is basically the paths that we're implementing. You'll see here we need, and I'll go to the board here. What we need today, I'll go here. What we need today, we need the function, the function that describes the dynamics. We need its derivative with respect to x, derivative with respect to u, and you'll see here these things come up here, fx, fu. We're going to need this. We're going to drop these quadratic, these second order terms. We're not going to do fxx and fxu. I'll talk about that in a minute. Then we need L, and L is our cost. And we're going to need L, Lu, Lxx, and Lux. So I'll write these down. We need Lx, Lu, and Lxx. And a lot of these are going to end up being 0, and Lxu, and Luu. And we'll call these from scratch. So we're doing everything from scratch. So that's it. And then these Vx's and Vxx's, we're going to just compute using the equations. So let's get to it. So first things first, I'm going to copy over what we had for our physics, so we're not going to end up re-implementing that. And I'll import what we need. So we're going to get NumPy. We do need NumPy. And first thing is, I'm going to use NumPy instead of, I'm going to turn off any code completion. We don't want that. We're going from scratch. We're going to use NumPy instead of my automatic differentiation framework. We might get to using that eventually, but for making it easier, we'll start with using NumPy. So first of all, we make this start at 0, 0. And that is our start state. Technically, this isn't needed for what we're about to do next, but it's nice to keep it here together with everything. And then we have our f of x. Now, because we're using NumPy here, all the calls here to tensors and all the arrays that we're using, the lists, they're gonna have to become NumPy. So we're a NumPy array. So we're gonna do this. We're gonna get NumPy.syn. These things remain the same, and then this becomes a NumPy array. So this is our state, and then here we'll actually do this later on, the unrolling. What we're going to do now is we're going to compute the derivative. So we need fx, as we said. We need fu. We need and actually that's it. Where we said we weren't going to do, so I'll say to comment, not doing fxx, fuu, or fxu, these second order terms, and these can be ignored. So we're going to do this in code. This is one of my favorite bits to do. We can do this by just copying this code and saying for each term we can do the derivatives. So we have a, and we need dA dx of 0, which is the derivative with respect to theta, and dA dx of 1. dA dx 0, du dx 0 is 0, so that's 0, minus the derivative of sine is cosine. So we have minus g times the cosine of x of 0. With respect to 1, this is going to be 0 because that's 0 and there's no 1 here, so this becomes 0. Because that's 0, we can just get rid of that. And so these are the dx terms. Now we need the derivative of the next two terms here, so we're done with this, so we can get rid of that. Now we need the theta dot nu dx of 0. And this is this thing, so this is going to be dx of 1 over dx, or over dx of 0, which is 0, plus dt, this is a constant, times dA dx of 0. And you can see here we already computed that, so we can use it. Again, we're going to get rid of the 0. Then we're going to do d theta dot new dx of 1. So here we have x of 1, so that's going to be 1. Plus, and again dt is a constant, times dA dx of 1. And we had a typo here. Right, I'm just going to double check that. Cool. So that's fine. Then we need the derivative, so we're done with this. We need d theta nu dx of 0. So again, this is going to be 1 plus dt is a constant times derivative of this dx of 0. And then we need the same with respect to 1. This is going to be 0 plus dt times this. So we can get rid of the 0. And then we just need to compact this in an array. So we'll get rid of that. And we're going to get a 2x2 array. And here we're going to Google Jacobian, which is the Jacobian matrix, just to check what our row or column layout should be. And so the standard is x's go this way and f's go this way. So that means it'll be with respect to x0 and then x1. So what was this? This was theta nu and then theta dot nu. So we get d theta nu dx of 0, d theta nu dx of 1, and then d theta dot nu dx of 0 and d theta dot nu dx of 1. Okay, so that's for our f of x's, and we'll check this using numerical differences or finite differences. Now again, we're going to take this thing and we're going to do it step by step. So in this case, it's dA du. This is going to be 1, and this whole term becomes 0 because it doesn't contain u. Then we need the theta dot nu du. This is going to be dt, so this term is 0, this gets removed, and it becomes dt times dA du, and then we do d theta nu du, this is 0, and then this is the theta dot nu times dt. And again, we use the same format here, but it's because it's one-dimensional, this is quite easy. We just use this. So I claim this is good and correct, and we'll check if I made any typos. The way we're going to check is to check our derivatives, use finite differences. And this is just the definition of derivative. Maybe I can go here and find the definition just by using Wikipedia. So this is the definition of a derivative, and we're going to use this to check our math. So we're going to say f with respect to x is f of x plus epsilon minus f of x minus epsilon divided by 2 times epsilon. And this is called a two-sided finite difference, which is more numerically stable than a two-sided finite difference. So instead of doing it like this, we add a small number here and we subtract a small number from the other one. So this is slightly more numerically stable than just adding one small number, because the epsilon here becomes very, very small. So this is what we're going to do. Let's just go back to our code, and this is going to be our finite difference check. Okay, so we're going to have a small epsilon, my minus 6 maybe, and then we're going to check this. Really, I'm not going to use this variable. We can check this 1,000 times over some random variables. So x is going to be uniformly random, and I don't mind what the range is here really. So we'll do x, and then u is going to be again a uniform random. I'll say this is minus 2 as well. This is size of 1, so x is 2 by 1, u is just a 1. So for x0, this is going to be x plus, and again we need to make sure we add our epsilon to x0. So we have 2 x's, u and dt. I will just copy this and I'll call this plus and call this minus, and this is minus. So then the derivative dx0 is going to be fx0 plus minus fx0 minus divided by 2 times epsilon, just like we had here. So that's our finite differences. And we need to do this for the two x's and the u's. So we have x's, and then we have u as well. So again, for the second one, we'll take 0 and epsilon, so the other x, leave this at 0. And for u, we don't need to do that, because we are going to add an epsilon. And u is one-dimensional, so we can just do this, and that's a bit easier. And that should be that. And then we just need to do the derivatives, so dx1 and du0. This is going to be a 1, this is a 1, this is a 0, and that's a 0. And now we also want our analytic versions of this. So this is just fu. This is what we're checking. Check our derivatives. And fu analytic is going to be, so this is fx, and then this is fu, fxu, and dt. And we just need to make sure that all of these are close, so dx0 to fx analytic. This is the x0 part of it, and we have some tolerance. we make this tolerance 1 to the minus 5, and then this is 1, and this should be 1, and this should be fu analytic. Okay, so we're gonna use Python 3.12, get a kernel up and running. This didn't work, did it? There we go. See if this works. And we have some assertion errors. Let's see if we can fix those. Okay. These seem to be the same. I might have some issues with the indexing, seeing as the numbers look quite similar. These two numbers do look the same actually. So I'm surprised that but they seem to be of a different size somehow. Yeah, so when you add them, you get that. So maybe there's a dimensionality problem here. Let's see. This is an array. 2 of 1 is what I'm intending to. Or sorry, rather 2, comma, and 1 comma. Okay, and then our state here for f of x is like that. Okay. So I'm assuming the du works here, first of all. Let's just check this. Oh, du doesn't work either. Okay. Why doesn't du work? Okay, fu analytic. It seems to be the same. Seems to me like we have shape issues when we're doing the these bits here. So maybe there's a shape mismatch when I'm defining the f function. I said this is size 2 comma and 1 comma. I'm surprised that. So I think I can do this, by the way, just to whoops, I can probably do this to make them work, but it's probably a good idea to fix our shapes. Yeah, so this makes them work. It's probably a good idea to fix our shapes and make sure there is no mismatch. I'm wondering if these plus and minuses have somehow made a mistake. So fx0p. So this doesn't look quite right to me. I wonder, yeah, this shouldn't be like this, because I'm returning here an array like this. So I wonder if, because I'm doing this, u as opposed to u of 0 here, I haven't messed up our shapes. There we go. Yeah, I was. So this is better. This is This is what we wanted. Yeah, okay. Cool. So that seems fine. Okay, so this is our dynamics now. Just double checking this is correct. Okay, so next up, what we need to do is we need to do the loss functions. And for our loss functions, we have, again, we're going to take them from here. So we're going to take these guys. These are our loss functions that were before, and we're going to change them to be in the format that we need. So first of all, we're going to do the weights. I'll say QF weight. The reason why I'm renaming this is because QF and QU also have a different meaning in the paper itself. So say QF weight and QU weight is going to be equal to 1e to the minus 1 from here, and then 1e to the 4th from here. So we need to define them in the format of L. Again, going back to our paper here, this is L, and we need its derivatives. So first of all, L is going to be, say, loss is QF weight times the cosine, or in this case, MP cosine of x is the last one of 0 plus 1, so same as here, basically, plus this number again times x's of minus 1 of 1 squared. So same as here. So we've done these terms, and actually I realize it might be easier to just tap that in and do it like so. And we'll say QU weight, and then we can just return that. So this is fine. For our cost at the last state, this is last state cost. This is last state cost, is this LF of here. We're going to say the derivative with respect to x is going to be QF of weight times, and this is an array again. So derivative of this is going to be minus sign, and this is 0. So we say minus MP dot sign of x of 0. Again, this takes just an x as opposed to the whole trajectory. And then for this bit here, it's going to be the derivative of squared. So we've got 2 times x, in this case, of 1. Just double check that. That should be fine. We do need the second order derivative, but this is actually quite easy. It's not quite 0. Some of them are 0. So again, we have 2 of them. We're going to go back to our partial derivative here. See the order. So x is this way and f's that way. So in that case, we're gonna go x is this way, so the derivative of minus sign is going to be minus cosine, and then we should get a 0 here. So this is dx of 0, dx of 1. This doesn't depend on x of 1, so get 0. And then this should be 0, and again, derivative of 2 times x of 1, well, that is just 2. So that should be hxx. Then we have lx at the intermediate states, lu, lxx, and luu, and lxu, or lux. And it really doesn't matter. All of these ones are going to end up being 0, as you'll see. This is going to be zeros of 2, because our intermediary only depends on the u. So really this is going to be 2 times QU weight times u, because that is our controls. This is going to be zeros, shape 2 and 1, because 2 with respect to x this way, 2 with respect to x that way, and 2 with respect to u this way. So no, LXX should be 2, 2. 2 with respect to x, 2 with respect to x. LXU or LUX is going to be one-dimensional u, two-dimensional x is 1 by 2. LXU is basically LUX transposed. Should be. Yeah. Okay. So then the only thing remaining is LUU. Actually, LUU and LU, I'll bundle them here. Actually, what I'll do is I'll bundle the x's together, so it's a bit easier, and then the u's. This is going to be 2 times QU8 times, well, 1, but we want it to be in the right kind of shape because these are all arrays. So we'll just say 1 like that. And this is 1 by 1. Maybe we might need to make a 1 by 1. I'll just make them 1 by 1. This is 1 by 1. Though my u's are, yeah. Okay. So the next step is to unroll our trajectory. And we can check these as well. I might check these later with finite differences. These are quite straightforward, much more straightforward than the dynamics. It would be a good idea to check them. So the next step is to unroll our trajectory, which is this bit here. We're unrolling our trajectory just like we did last time. So we'll say we start at x of 0, and then no nodes this time. We'll have a array. I'll make it one-dimensional. Actually, if I make it one-dimensional, okay, and we'll start at 2, and then we'll append some u's, and then we'll call our function again. Did I not? I do have x of 0 here. Maybe I wasn't calling that. But, yes, I suppose I must have restarted that. I do need to. Why is x of 0? Oh, x of 0 is not an array itself. X of 0 is just, yeah, okay. So then we're going to copy our plotting code here. I'll put this down here. I think I'll need matplotlib as well. And since this was using my library before, now it should be like this. Hopefully this works just fine. And then we'll see that it's going to go to the right and then kind of get stuck a little bit. So yeah, here, because we're not actually doing the controls. Okay, so now it's time for DDP itself. And DDP itself is going to be these equations going backwards, and then this equation going forward. And I'll explain them each as we go along. I'll try and do it as much as I can in the code itself. Okay, so first of all, I'm going to make these arrays for our k's, and this will become, we'll see why we need them in a minute. So these are our gains. DDP gains is what they're called. So we have one for a big K and one for a little k. And then I'm gonna pause this. Then we're gonna go, I also need some regularization, and I'll say what that is in a minute. So then we're gonna go for each range of, for some number of iterations. I'll call this 100, but I highly doubt that we're gonna need 100 iterations. And then we're going to do this pass backwards. Actually, probably a good idea to print our loss function. Let's see, it's not loss, it's L. Let's see what that is. So that's our starting loss. Okay, so first of all, we have Vx and Vxx. And these things are, as we go here, these things are these things. So Qx and Qxx are the last states, are going to be just our Hx of our last state and Hxx of our last state. This is our starting Vx and Vxx's. And now we need to go backwards in time from t-1 to 1 and compute all of these matrices. I wonder if I copy them directly, whether that will render well. Not at all. well, I'll say qx, actually I'll say here x, u is x's of u's, these are our states, the time step. So now compute qx, qu, and so on. So we say qx, and we can literally just read it like that, lx of x of u plus fx of x of u. So I know what this is, but it's this component, dt transposed matrix multiplied by vx. Vx prime means Vx at the previous state, but it is the previous state. As you remember, this is at time t basically. So yeah, so we are ignoring the last one effectively. Cool. So then we have Qu is, and again, it's a very similar formula, Lu of x and u plus Fu of x and u and dt transposed at Vx again, and we're ignoring the second order terms, so I'm just going to write these down. Qxx is a Qxx first here, yes. Lxx of xu plus fx of xu and dt transposed Vxx. We can make a little optimization here if we want to by using the walrus operator and f of x, and so on for the other two. I'll just copy this just to make our code easier. UU, and actually I should do XU first, and then we can store the stuff. So because it's x of u, this will be f u. Actually, it doesn't really matter if it's hang on, we have u of x, not x of u. So we'll do u of x. This will be u, and this will be that f of x that we stored here. And then when we get to uu, we can just reuse f of u. Actually, we can just reuse. I'm just wondering if the transposes are gonna bite us a bit, because I should probably just say like this, just to make sure there's no transpose madness going on. And then this I can get rid of this actually. So this is okay. So f of x, f of x, f of u, f of x, f of u transposed, f of u. Okay. So then we compute our gains. So k is, and you see here that the definition of the k is the inverse of this matrix times q of u. So we'll do clean out dot inverse q and this is where my regularization comes from that I define up here. Whenever we invert a matrix, we should do some regularization. Matrix multiplied by qu, and this is qu of -1 qux. So I'll copy this, capital K, again same inverse, and we can actually do a little optimization here as well. We'll store the inverse so we don't compute the inverse twice, which is usually a thing we should be doing anyway. We'll store our k's. So k little one, we'll need them later, and k big K, k's. And then the only thing left to do is to compute these things. So we'll do that as well. Compute Vx, Vxx. So Vx is equal to, and we can just copy this, Qx minus K, big K transposed, multiplied by Qu multiplied by little k. Yes. Okay, and then Vxx is going to be Qxx minus K times Quu times big K. And it says here actually this bit here that where we initialize it at the last point, the last bit here was also mentioned in the paper. Just realized I didn't say this. I'm wondering if okay, and normally, and this is something that's not mentioned in the paper, normally we're gonna regularize a little bit the Vxx as well. So we use this U regularization here as well for our Vxx. Okay, so we've done our backwards pass, and now we have a forwards pass. And this is the next bit in the paper here. The forwards pass tries to update our controls with a little line search parameter. So it'll do something like, it'll try different values for this k and only keep the ones that minimize the loss function. So we start at some loss. This is our initial loss. And then we say we need to have a best alpha and some candidate x's and candidate u's, which currently are just our current x's and u's. So try and find an alpha that minimizes our cost. So we say for alpha, we'll start at 1, we'll end at 0.01, have 25 alphas. And then for each alpha, we're going to do this, and we're going to compute, well, see if we get a better one, and then find that. So first of all, let's do our exit conditions first. So if best alpha is equals to 0, this means couldn't make loss smaller. Increase regularization is actually what we're going to do. We're going to say that ureg is going to be multiplied by 10, except we don't want this to grow up to infinity, so we'll say and ureg is less than something big, by 1,000. If we're regularizing too much, then just let's not do this anymore. So then if best alpha is equals to 0, and we can't do this anymore, then here we're done. Either convergence or ureg too high. Actually, it's not convergence here. It is ureg too high normally. So we'll say iteration, whatever. Actually, we're not even keeping track of it. Oh, no, we are keeping track of iterations. Good. Loss, no improvement. Okay, so we'll say exit like this. Then we have the condition of ureg is really, really small. This usually means convergence, but not real convergence check, because I'm lazy. So it's not a real convergence check, but break because ureg too small, and then we'll just break. And reduce ureg if iteration successful, and we'll say ureg is divided by 10, and we will append our losses as well. Sorry, us is divided by 10. We need probably somewhere to keep our losses, so we can plot them, and then I'll just have a print statement here, which will be just my normal iteration print statements. Cool. Okay, so now let's do our forward pass once we've done this. So for our forward pass, we'll say that we'll start again at x0, and then basically it's this thing once again, except our u's are computed using the formula from the paper here. So let's do this. We are gonna do, instead of uval, we're gonna get rid of this, and we're gonna say use of I plus alpha times, and again, alpha kx plus the big alpha times the difference. So alpha times k's of I plus the big K, matrix multiplied by, hang on, I need x is nu of I, x minus x's of I. Isn't that? Yeah, okay, so the reference here is the old trajectory, and then the other one's the new trajectory. So something like this is our u's, and then we append the u's, and then we append for the x's. I already have this. Not x's, but x is new here, and that's a new x's. Then we have calculate loss. Loss new is our loss out of x is new, u is new, and if it's better than our loss, then we have a new candidate. So we say candidate use is use of new. All right, candidate x's, candidate use is equal to x's new, use new, and then our loss is our new loss, and our best alpha is alpha. Let's see what errors we have. Okay, so first of all, we have an error with our hxx's. Let's see what we've done here. We do not have an array here surrounding that, so that's quite an easy fix. We might have a few of those errors. I is not defined because it's a t and not an I. I is not defined again. Okay, there were all I's. I'll use t because it's time. That makes sense. And here, let's try this again. List index out of range. We do have the 0 one. I wonder why. Why is x's new of t? I mean, I can do this. Okay. This thing failed. Why did it fail? It failed after my passes though. It worked fine here. We did get an initial loss. Actually, I'm gonna print this as well. I'll say initial loss. Now it's time to debug. I'm gonna change the title, maybe. Let me just change the title here. Debugging. Now it's time to debug our code. Loss is not callable. This is an L, not a loss. So let's see. Okay, loss plus equals Q weight is an issue in our function because we've done something bad with the use. Let's see what our use new look like. They don't exist. Ah, this is my problem. I'm appending to our existing array. That is definitely a problem. So we're gonna do this again. Okay. Loss new is an array. Why is loss new an array? Well, first of all, why is loss an array? Hang on. Loss is an array. This should be of 0, I imagine. So I debugged this for a while. Had some shape issues here, which was one of the problems. This should have been shape of 1. Then the other issue was that I wasn't actually saving, that I wasn't restoring the candidate use, so we need to do that as well. I think with these saved, it should largely work. So things are happening. Let's get rid of some of this annoying printing that I'm doing everywhere, like this. So let's see if we can coerce this to work. Once again, I am printing loads of stuff that I don't want to be. Where am I printing things? There's some prints that we want to get rid of. Oh, okay, that's fine. Okay, so now the loss is being reduced. We're gonna copy our plotting code just to see what exactly happened. Should be fairly easy to do. I'll put it after here. No vowels, just 0 and 1, and again no vowels. So let's see, what do we get? Do get some controls. Now I wonder if we plot our losses, if we've converged. We haven't converged. Actually, we should probably move this into here. So it doesn't look like we're converging though. I don't know if having more iterations is the way to go. Ah, certainly seems like we are converging now. Looks like we're nearly there, if not already there. Which which means that we can say we have finished. Done. That does look quite good. Let's restart, clear everything, and run all. And let's see what we get. It does seem to be quite a fast convergence, which is what we're trying to do at the end, in the end of the day. That is quite cool. And that looks like it is the implementation that we were looking for. So, a couple of important parts here. This is quite tricky to get right. I had to actually stop the recording and go through it bit by bit. A couple of important bits that aren't in the paper is regularization of VXX. So I'll go here. We want VXX regularization. This is important, and not in the paper itself. We want to have U regularization actually also for VXX, and this repeat iterations and increase. So basically, or rather increase and repeat iteration. So the point is that if we don't have an improvement in the cost here, we do increase our regularization and we go again. And if this becomes too small, then we just say, well, we can't do any more. So we're saying convergence. We can make this really small and get it to converge even better. The point of this is that it's significantly faster than using our previous method. Firstly, because it uses quadratic approximation, and secondly, because the computation of the derivatives is done like this by propagating exactly the things we need, rather than using the automatic differentiation framework that propagates a bunch of stuff we don't need. I think at the end of the day, if you simplified this, it would be very similar in terms of math. The second order terms definitely help. We did say we are ignoring these bits here, which we can include if we wanted the second order derivatives. These will become three-dimensional matrices. We can do this as well. That should improve convergence, but also might slow individual iterations. So I have a reference implementation here, trexdiff, that does do this in ilqr in my automatic differentiation framework, and I'll just finish it by talking a little bit about why this is a nightmare. So the reason why this is a nightmare is because we need to use a tensor 2D object, and the tensor 2D objects are not that great, meaning that we have both a node and a tensor object. So let's go here and let's talk about trexdiff. What we have there is we have a node class, and that node class is backed by a tensor object here, tensor 2D. Why are these so small? I wonder. Okay, so there's a tensor 2D that backs the node objects, and the problem with this is that every time we have to instantiate a node, we also have to instantiate a tensor 2D object. So you'll see here in the code that there's a tensor 2D object. Actually, probably better to look at the header files. So we have a node class, and each node has a bunch of tensor 2D objects that is backed by. And so we have a bunch of functions to add nodes and multiply nodes and so on, broadcast nodes. And then there's also the same stuff, exactly the same stuff in tensor 2D. So we end up re-implementing NumPy essentially, which is not what we want to do. In fact, what we probably want to do eventually, and this is what I'm going to think about next week, is we want to make this a single class that doesn't get backed by tensors, and all of the operations are basically just not operations to compute the automatic derivatives. This did help last time, because we could also do eager evaluation, so we could evaluate arrays directly, as well as, or we could do tensor math, as well as we could use nodes for automatic differentiation. But unfortunately, I think it's just too much. So we're gonna get to that, I think, next time. But for DDP can be done directly in NumPy and not that many lines of code, just by following the paper. It is one of the nicer algorithms. There's a bunch more we could do here. The paper actually goes on to formulate these, so these inverses here that we did, as here, formulates them as quadratic problems, so we can do better here. But I think we're gonna finish it there. I'll put up the code using trexdiff in the library, and for a bit of a different video, we implemented a paper.